welcome. We got a lot of material, so we're going to blaze through this. Hold on. It's going to be quick. So my name is Matt Porter. I'm with Consulco Group. And if you're looking for Alan, I'll explain on the next slide why I'm not he. And you can probably tell, because if you know Alan, he's got hair down to here. So this is an introduction to memory management, and I stress introduction. So if you're an experienced kernel person, you might not get as much out of it. This is the presentation that back when the early adopters of embedded Linux back in 2000, 2001 were coming in from working on RTOSes. I wish I had sat down and put something this good together, because these are the things that everybody needed to understand to really grasp their system. All right, so just real quick about the original author, Alan Ott. He couldn't be here, unfortunately. Good friend of mine, and he's a veteran embedded Linux developer. He's a Linux architect at SoftIron. You may have heard they're an ARM server company. But he put together all this material. He's a fellow instructor, LF training instructor. Also gives the kernel internals class that contains a lot more than this material. So he did a really nice job on the slide deck, and trusted me to present it as well. So anyway, just want to give him the kudos for this awesome material. So here we go. We're going to talk about memory management from the beginning and the end, and it's going to be the intro, as I said. So we start at physical memory. If you look at your low-end systems, they have a single address space, and memory and peripherals are sharing that same space. They're mapped into different parts of that single address space, and all the processes in OS in this type of system share the same memory space. There's no memory protection like you would often hear about. And we're going to get into all the details of this. And you're running a process in that single address space. Processes can stomp on each other because they're all shared in there. You have to separate them manually. And, quote, user space or your user application can stomp on, say, your real-time executive that you're using to schedule. So examples of these would be an 8086, Cortex-M part, AVRs, all these low-end microcontrollers in the old pre-MMU processors. So let's take a look. So it gives us, I know a lot of us are not working on x86, but it serves as a ubiquitous example. If we look at a 32-bit x86 system, right? Lots of legacy, obviously, but it is a common ground. We have all of these legacy areas and so forth. You have hardware mapped between RAM areas. You can see that your PCI physical PCI area memory mapped I/O is all in the high part. Okay, so that gives you an idea physically what x86 looks like. Now, what's a limitation with the single address space, right? You have portable C programs expect that they kind of own the whole thing, right? They don't know if you're trying to port several C programs into one space. You've got to go set the addresses. This can live here and this can live in this segment, so they don't stomp each other. So it's kind of hard to do that. You've got to have special knowledge of your actual platform. You need to know what your total RAM is. And you need, as I'm saying, you need to separate those processes. So you have to do all this work. And there's no protection, right? As we said, rogue programs can stomp all over things. So in comes virtual memory, and this is where things get fun. So what is it, right? It's a mapping. It's a virtual mapping, hence the name virtual. So, so you map a virtual address, a fake address, to that physical address. All right. When we look back at that x86 map, that's all physical world. And if we can just think in virtual addresses, we can have any mapping we want. So we map virtual addresses to physical RAM, but we also map virtual addresses to hardware devices, right? So PCI, GPU RAM, on SoC IP blocks, right? Everything. So what's the advantage, right? Described how in that flat memory model, the single address space, we have a situation where, you know, I got to tell something to run at this address and this address and this address up to n times and actually have a nice memory map of where everything lives. It's not portable, right? So when we have virtual memory, right, you have one process's RAM is inaccessible to the other processor. It's also invisible, right? So you have built-in memory protection. And kernel RAM is not visible to user space directly. The nice thing you have is that memory can be moved, right? So memory can be visible to different processes, but you have to actually set up a mapping for that. And the other nice thing is, rather than in a single address space where you have all the memory sitting there and you have to manually share it and segment it, right? You can now do things like swapping memory out to disk because the addresses you're dealing with are just virtual. The other thing you can do with virtual memory is map that hardware, right, that we talked about can be mapped into your process address space, okay? We need help from a kernel to do that on behalf of user space, right? The other thing is we can take RAM memory and we can map it into multiple processes, right? And we're going to get into that more, and that's the shared, that would be a case where, like a shared library, right, where you're mapping it into multiple processes. And finally, with virtual memory, we get the ability to have read, write, execute permissions placed on those address accesses. All right, so we have two address spaces now, right? We've got the physical addresses we talked about, and we saw that physical memory map, x86 we use as an example, and that's, you know, DMA, peripherals, whatever it maps out to in your physical world, right? Virtual addresses, right? And those are the ones that our actual software uses, right? When we get to our machine code, whatever architecture, that's our load store accesses, right? Out to memory, and those are always using virtual addresses. All right, so looking at virtual memory, right, we have to do a mapping. This mapping is done in hardware, so there's a piece of hardware that assists with these mappings, okay? Once we have it mapped, there's no penalty for accessing memory that way, right? The permissions are handled without a penalty. So this is all handled in hardware for us, and we're going to talk about what that hardware is that does this. And of course, we use the same CPU instructions, those same load stores, whether it's RAM or a piece of peripheral I/O. Okay, so in normal operation, you're always using virtual addresses. All right. So what magic does this? It's the memory management unit, right? And so an MMU sits between the CPU core and the memory, all right? It's often, in a modern architecture, part of the physical CPU itself. If you look and like retro things, you'll find that MMUs used to be a separate, discrete part, right? And were interfaced and were part of that set, sold just like, say, a PMIC. Is often an integral, separate, discrete piece of a architecture. So the one thing to keep in mind is that the RAM controller is a separate piece. So you got an MMU. The DDR controller is going to be a separate IP block, tightly coupled though. And what does an MMU do? Right? What it does is it just does that magic of transparently handling the translation of those load store instructions into physical addresses, okay? So we map the memory accesses, the virtual addresses to our system RAM, that physical address space we talked about, right? Same thing with peripheral hardware, it's no different from its point of view, right? It handles permissions. You said we got permissions with virtual memory, and if we have an invalid access to something, it's going to generate an exception. And with that exception, we can go do some interesting things. And we'll talk about that in a bit. Okay, how an MMU works. There's an important piece of the MMU called the TLB, translation look-aside buffer, okay? And so that's just a hardware buffer that has a set of mappings, and those are your virtual to physical mappings. It'll have permissions for that space, okay? And there's a granularity in which these mappings are kept, and we're going to talk about that in a moment. And the interesting thing is that, you know, TLB design is very architecture specific, very part specific, performance sensitive, and so you'll see a wide variance in how TLBs are designed, how mappings are placed in, if it's software done or it's hardware assisted, that type of thing, and also capabilities, how many slots they have. All right, so this is a quick little diagram of what a system looks like. If you're having trouble visualizing it where it sits, you see the MMU between the memory controller, right, and the CPU. You see that TLB on the side with some entries, okay? All right, so as they're saying, with that TLB, the MMU takes a look at that buffer, right? Is there already a mapping in there when it accesses a virtual address? And then it can look that up, and if it doesn't find one, then it's going to generate the page fault, interrupt the CPU, okay? Now, if the address is in the TLB, but let's say you're doing a write access, but it's only set for read permission, it's also going to generate an exception. And that'll come back into play as we get into how we use those things in Linux. So in Linux, a page fault, right? So you have a CPU exception generated, okay? And this happens when you access that invalid virtual address. What makes it invalid, right? It's not in the TLB, okay? And you have three cases. So first, virtual address just isn't mapped, okay, for the process that's requesting it. Second, you don't have the right permissions, right? And third would be that it's a valid virtual address, but it's currently swapped out. And that one's a software condition. So let's dive into, we're going to dive into each of those, but first we're going to get into kernel virtual memory side of things, okay? So we use virtual addresses both in the kernel and user space. But the way that we use them, how things are mapped, are quite a bit different. So in the kernel, we use them obviously, but we have this split in how we treat our virtual addresses. The upper part of our virtual memory map is for the kernel, and the lower part for user space. And usually when we teach people about this, it's harder to think with 64-bit addresses, so we go back to 32-bit, and we affectionately call the default spot that it's split between user space and kernel space is C bazillion. That's at that 3 gig location. That is a default. So this is what it looks like. So you saw that hugely complex physical memory map of x86 32-bit architecture, and lo and behold, here's the virtual memory map. We've got 3 gig for user space, right? Config page offset controls where that split is set at, right? And so every process gets its own 3 gigabytes in that system. It has that whole view. So you remember to go back to that single address space. If you had multiple processes, you had to go link them in all these different spots and manage your processes very manually. In this world, when we link applications, they all end up at the same place, right? And the kernel just has this 1 gig in our 32-bit case. Okay, so as we said, that config page offset controls that. A lot of architectures, if you have specific needs, you might fiddle with that a bit. That sometimes happens in embedded stuff. On 64-bit, we don't have this situation where there's ever a possible need to do that, essentially. On ARM64, we're at 8 bazillion there. x86 64, the splits at a different location. You know, given RAM sizes and so forth, it's effectively something that's not worried about. In a 32-bit system, where that page offset is has an effect on how we deal with large memory systems, which we'll talk about in a moment. There's 3 kinds of virtual addresses in Linux, and LDD defines these best. You can look at that, and the way we define them are, and some people use some different terminology historically, but in the kernel side we have kernel logical addresses, kernel virtual addresses, and then we have those user space virtual addresses. Okay, there's another special case, but most people don't speak about them exactly that way, either physical or bus addresses. But you can look at LDD3, the link was in there, for a little bit more information. So kernel logical addresses, that's what people consider the normal address space that they're normally dealing with. What you get back from kmalloc is a kernel logical address, okay? They have a fixed offset, okay? And you see a magic number there, that's the config page offset value, and that would map to that. Now that physical address is specific to one architecture. That could be wherever your base of RAM is, and it does get more complicated in various other segmented memory systems, but this is an introduction, so we keep it simple. Because this is a very simple mapping, logical mapping, the conversion's really easy to do. So visually it looks like this. Your kernel logical addresses are at page offset. Point down, assuming your physical RAM in that physical memory map starts at 0. Boom, you've got this very simple logical thing. And accordingly, you have a very simple set of macros that can convert when it's a kernel linear or logical address. Okay, now the next thing that's interesting when we have a small memory system, right? So we'll call them small or large, and this is really specific to our 32-bit example. Okay, so less than a gig of RAM. It's technically less than that, really, when you look at where the split's at. You have those kernel logical addresses, right, starting at the page offset and then going through the end of memory. So if you had 512 megabyte, okay, then you would have C up through D, all foxes, right, would be that kernel logical area. So it's very simple when you have that small amount of memory. That's where it gets mapped into kernel logical space, okay? So things that it includes in logical space, like we already said, allocations with kmalloc, get free pages, all of those allocators, and kernel stacks. The key thing here is, and we haven't talked about how swapping works yet, but logical memory can never be swapped out, okay? There is, as we said, there's that fixed mapping. We saw how simple the macros were for that, okay? But because of that, everything in that kernel logical area, it's all physically contiguous. So that's important because we need that for DMA. So that's why you'll see kmalloc and those types of allocations used with DMA-able buffers, okay? Okay, then it gets complicated. If you're on a large memory system, something more than a gig of RAM nominally, right? We run out of space, right? Our page offset was at C, but how are we gonna map that all into kernel? We can't, okay? We run out of room there, and then on top of it, we have to have the space for use by vmalloc memory, which is our kernel virtual address range, and we need to keep that. So we're going to talk about that in a moment, okay? Once we go above that gig of RAM, nominally it's actually less. Then we have stuff mapped into the kernel virtual memory area, and so that's the high mem support. again, note that when we're taking the 32-bit model, we have that problem. With 64-bit, we don't really effectively have that problem until we're going to get ginormous amounts of RAM on the system. Doesn't seem like it's going to happen tomorrow in that space, okay? All right, so kernel logical mapping, right? We saw page offset. And then in this large mem system, right, we don't have enough room for that. So the additional RAM is going to be mapped separately in that kernel virtual area. So you don't have that logical mapping. So those things you can't use any of those simple macros on them at all. Okay. So how do we call that? Low memory is that directly mapped set, right? And then the high memory there is not physically contiguous. It gets mapped in on demand. We only have that situation on 32-bit. And the key thing on the low memory, as you saw, and you can see it visually. You go back to these sections that you have that one-to-one mapping there, right? But the rest of it, you do not. Okay. So let's talk a little bit more about kernel virtual addresses. So the easy part was that logical set, very simple, right? So kernel virtual addresses, I usually call it vmalloc space, like a lot of people. And so keep in mind of that. And that's that area above that logical range that's managed dynamically. And so those are used for non-contiguous mappings. So what's the practical case for that? InsMod, right? You load a module, memory is allocated. It needs to be virtually contiguous for that module, but doesn't need to be physically contiguous, right? So what you'll find is the module does vmalloc. It's got that virtually contiguous area, and but the actual physical backing RAM could be scattered anywhere, okay? The other piece is memory mapped I/O. You're using I/O remap and friends. We'll get into that, right? That also ends up in that space. So, all right, so quick look at that. We've got logical addresses, physical RAM. Whoa. And so that's what that looks like, and then you've got your virtual address space up there, right? Your modules are getting installed, your I/O remaps, all of that. All right. So keep in mind, as we said, that the key there is it's non-contiguous, right? You can't rely on it for DMA at all. That's the main point here. All right. Let's go over that. Yeah, so this is reiterating, probably maybe too much, is this emphasis that on the 32-bit machine, right, we have a very constrained space in the logical address space if we have 768 meg of RAM. Okay, so there's less space for kernel virtual addresses. So those are tunable, and you just don't deal with this problem on a 64-bit system. All right, so let's jump into the meat of user virtual addresses, because this is where it gets more complicated. So our user virtual addresses, right, that's what our applications or our processes are mapped into. Okay, they're all below page offset. If you remember that memory map we saw below the 3 gig mark in our modeled 32-bit system, right? And each process has its own mapping. What I mean by mapping is its own view of virtual address space, right? A thread shares mappings, and things get a little bit more complicated with clone because there's a lot of options, and you can choose how much you're sharing and so forth, but that's beyond intro level. So one of the key things is kernel virtual logical addresses, right? They have that fixed mapping, okay? User processes are fully using the MMU. And the only time that you actually use RAM is when when you're actually touching it. We'll get into that, right? The memory isn't contiguous. It's a lot like that vmalloc space in kernel. You can't rely on anything being contiguous just because it looks that way from the virtual address, right? And the nice thing is you can swap out. Remember, kernel logical virtual addresses, it's not swappable memory. And the memory can be moved around on you. So that's virtual world. All right, so what does this fundamentally mean? Since things can be moved around on you, it can be swapped out, you can't use it for DMA, right? You can't allocate, you can't malloc memory and then try to DMA to that virtual address, all right? It's not going to be a stable backing behind it, all right? Now, how does this work? Every process has its own memory map. You can go look at struct.mm, right? There's pointers to that in your task struct for your process. And that's where that whole mapping is kept of those pages. We'll talk about pages in a moment. Every time you do a context switch, that memory map gets changed. And that's where that overhead comes, right? Your context switching overhead, where you have to go change that mapping, okay? So again, back to our map here. We've got this view of the 32-bit world. And every time we change the process, this whole set of mappings in here into this space is going to change. So back to the MMU, right? So we use that to manage those virtual address mappings. And so I already hinted at page. So how does this done? It works on the granularity of a unit called a page, okay? And some architectures, people always hear 4K. Some architectures, most architectures, they're configurable. There's some advanced features, some very large page types. We're not going to get into that today, but here's some common ones, right? 4K, 4K or 64K on ARM64. Like I say, we're not going to talk about huge pages. That'd be a more advanced topic, but let's just assume 4K for this talk, since that's what most architectures are defaulting to. So that's our unit of memory that the MMU can work with, right? We're aligned on that page size anytime we do any allocations or mappings, all right? And then we have this concrete concept, which is the page frame, okay? And that's page size, page aligned unit of memory, of physical memory. So anytime we say page frame, that means in that physical memory map, okay? And when we talk about a page, that's the unit for virtual addressing purposes that the MMU is dealing with, okay? And so you'll see that abbreviation PFN throughout the memory management code. That's your page frame number, right, referring to that page frame physical unit. Okay, so MMU operates on pages, right? Memory map for a process is going to have this huge list of mappings, right? Big space, a bunch of scattered page frames all over the place, right? A range of multiple pages. And so what does the TLB need to know, right? The TLB, when it actually gets loaded with a mapping, right? A virtual address, the physical address, so page frame, right? And then a set of permissions, right? Read, write, execute. Back to our view of that, right? Just as a reminder. All right. So as we touched on earlier, if we access a region of memory, right, that we don't have mapped, we're going to get a page fault exception, okay? And this is normal, right? These are good things. We want this page fault exception, okay? And I mentioned that TLBs vary in size. You know, some of the embedded stuff, they have 16 entries in it. It's not much when we know that our page size is 4K, right? And so that's got a lot of churn in it, okay? And so when we context switch, we have a lot of page faults as we start touching virtual addresses that aren't mapped, right? So your process gets swapped or context switched in, you start executing code, it's touching, you get page faults, that exception because we don't have a mapping, right? And we also have a concept of lazy allocation we'll talk about in detail here. All right, so this is what it looks like visually. In between, you've got your virtual address. It's hitting the TLB, and then it's able to touch those physical page frames, right, through those mappings that are set up, right? So mapped page ranges, right? So contiguous set, say the text for your application, your process, some data area that's mapped, and those are going through the TLB to access actual backing page frames for that area. And then you'll have some unmapped space that maybe hasn't been executed yet. Notice that's the allocated frames on that side that's going through there. All right. So just as I mentioned with kernel virtual addresses and that vmalloc space, it's not guaranteed to be contiguous, okay, in user space virtual addresses, right? So don't rely on that. We already said that's why you can't use them for DMA, right? And one of the reasons for that is it makes it much easier to allocate memory. If you get into how the internal memory allocators work and think about how fragmented things get, this allows you to go put together a large allocation with a lot of scattered page frames, right? And almost everything you do, it doesn't require physically contiguous page frames backing your code. All right. As we were saying, when we looked at that virtual address and we said the virtual address space, say in 32-bit and that 3 gig area, we said one of the cool things was that each process gets its own address space. So what does that mean? You hear that all the time. It means that when you look at the virtual address space and say you look at that task struct and that MM, you're going to see mappings that have that same virtual address, but they're pointing to all different physical memory addresses all over the place. So if they're in there at the same, if you have things scheduled running next to each other, they're using the same virtual address, right? They get scheduled in, but it's mapped, right, to a different page frame each time. So, but they don't have to know about that backing. And so here's an example, process 1 with this set of virtual addresses mapped through all these different page frames, right, in the blue. And then process 2's got these same virtual addresses, and he's touching completely different page frames, right, just visually representing that, okay. Now we get into shared memory, right? We need to, for IPC purposes, shared memory is a common concept, a POSIX concept, normal concept in most OSs. and so shared memory using MMU, and we saw how we can have the same virtual address with different page frames, right? We can have different virtual addresses pointing to the same page frames is essentially how shared memory works, right? So simply map the same physical frame to different processes, right? The virtual addresses don't have to be the same. And now you have shared memory, right? 2 different processes, completely different virtual addresses, but they're touching that same page frame as they get context switched in, okay? And how does that look? We got the shared physical frame down there in green, right? We've got this virtual address mapping to it. It's touching that shared frame, right? This is a 4K shared memory space. And then this completely different virtual mapping and the other process pointing to the same frame. Boom, we've got shared memory. So that was the case with different virtual addresses, okay? The mmap system call you may be familiar with, right? You can get at a specific address to share the memory. So that's a different case, okay? And it can fail. All right, let's talk about lazy allocation. So one of the things you will notice when you work on a Linux system or a classic Unix system is that the kernel's not going to allocate memory directly. Well, yeah, you saw your call actually come back successfully, right? You got virtual memory, but it didn't actually allocate the physical memory, those page frames that back it, right? And that's what we call lazy allocation. So there's an optimization, right? The kernel is going to wait until you actually need to use that memory. So if you're allocating a 4 megabyte chunk of memory for your database and you haven't touched any yet, it didn't really allocate anything for you, right? If you never use it, you never touch it, it never allocates anything. All right, so how does this work? So when we request that memory, it just creates this record of the request in the page tables. We'll talk about page tables in a moment. Returns the process, and so you've got that virtual memory set aside in the user space process, okay? Once we touch it, our old friend, the page fault, comes into play, right? We already learned that we're going to get an exception, right? Because there's no mapping there, right? Or it's only set to read permissions, right? And we're going to go do the page fault handler. So kernel's going to use page tables, see that the mapping is valid in this case in a lazy allocation, right? Allocated virtual address space, but it's not yet mapped in the TLB, okay? At that point, it's going to allocate those page frames, a page frame, a series of it, whatever the request needs to be satisfied with, okay? And then it's going to update the TLB. It's architecture specific how that happens, of course, with that mapping. And then he comes back from the exception handler, and the user space program continues. So your malloc got you that virtual address space and returned quickly, but when you went to touch the memory, all of this happened behind the scenes, right? The first time you went to dereference that pointer and update it with a value. So that's what's happening behind the scenes, okay? But you're not aware of that. Key point here, right? But you will see it if you're running benchmarking and you see that lag, right? It's appreciable, right? And you can use tracing tools and see how that's happening visually. The other thing, if you have time-sensitive things here, right, you know that you have a fast path, you can go pre-allocate that. You may have used mlock or the family mlock calls. That will go ahead and pre-allocate these things so you don't have that lazy allocation situation. So as we said, getting into page tables, TLB entries could be, the entries in the TLB can be a limited resource, right? We can't just map the whole world of our address space in there, right? We have a lot more mappings in that struct for our process than we have TLB entries, so the kernel's got to track all that. So it has a set of data structures we call the page tables, okay? And you can look in struct and VM area struct to see how those are done. And, but it's essentially a hierarchy that leads you down to that 4K page, right? And the associated mapping to a page frame number and the permissions, right? So everything lines up with what needs to get loaded into the TLBs, okay? And also has metadata in addition to that about is it valid or not and so forth, and some other housekeeping flags as well. Okay, when we have something in the page table in the TLB, so we have a valid mapping, right? And you touch it, the hardware, since there's nothing in the TLB yet, is going to generate that page fault, right? CPU doesn't have the knowledge. CPU, the MMU, right? Only a kernel does. All right. So our page handler runs, right? It's going to traverse these page tables, find that mapping for the virtual address, right? Page granularity, select and remove an existing TLB entry, create a new one with our address and the correct permissions and so forth, and come back to the user space process, okay? All right, swapping. And, good. All right, so swapping. We're used to our systems. We deal with our desktop systems, our development systems, where we have a lot of swapping out to our disk when we're doing heavy builds, right? Running low on RAM. And you know, how this works is the MMU is the thing that enables this, okay? And So you're going to run out of that 16 gig RAM you have under these heavy builds, and you're going to context switch, and it needs more memory, and it's going to take those page frames that were backed, and it's going to take the contents of those, and it's going to push them out to your storage, right? And then when you need that data back, and you've been context switched back in, it's going to read that back off that slow storage and bring it back in. That's the big picture, right? So low-level details, right? It's going to do that on a frame-based basis, right? It's going to copy a frame to the disk, remove the TLB entry, and then that frame is free to be backed for another process, right? So when we need it again, right, CPU generates page fault, right? Common theme here, right? We flush that entry out of the TLB, right? So now it's going to generate a page fault, and then when we hit that page fault, the process sleeps. We copy that frame from the disk into an unused frame, and we update that page table entry, and then wake the process back up, okay? So it's going to be a slow process, right? We got to go out to that block I/O. We're throttled by that bandwidth now. So when we restore the page to RAM, okay, we're not necessarily getting the same page frame. So again, we have this virtual dance going on here, right? There is no persistence or affinity to that original physical page frame. So you need to get rid of this notion that physical addresses matter, okay? You will use the same virtual address though, right? Because those mappings stay the same in user space, all right? So you don't know the difference. So your code's executing along, you yield the processor, it gets swapped out, you context switch back in, it'll redo that mapping, same virtual address, and your code continues on at the same virtual address, but a completely different backing as the page frame context gets copied back in and then mapped in, okay? Again, this is that low-level detail why we said we can't use user space virtual addresses for DMA. We have no persistence of the physical backing that the DMA engines and the peripheral hardware need. All right, so what does this look like visually? We've got this frame that was selected by the kernel to be swapped out to our disk. We've got this wonderful trash can looking cylindrical disk thing here, and we copy that frame out to the swap media. We invalidate the TLB entry. The page table entry is invalid now, right? Okay, and now there's no entry there, so that frame's freed up. So now you can free it back into the allocator pool, but the data is preserved out there on disk. That's in your swap partition, right? All right, now we get context switched back in, right? We're back and running, same process. We try to access that same virtual address we were just running when we got so rudely taken off the CPU, and we get the page fault thing. We've been through the page fault dance before, and we just rock on through that. We get copied from the swap, this cylindrical, simple disk thing, and put back into that page frame that we got allocated. Create the TLB entry. Thought I had one more animation, yeah. And then we return to user space. Now we can access that virtual address. We've got the same data we had before we got swapped out. All right, so I'm actually running this on time behind, so I win. All right. It's 95 slides. So user space, we got several ways. So we've been through that whole stack, all the major pieces of how everything's happening in the background. Now let's see how this maps into our APIs we have in user space, right? And so we have several ways that we allocate memory, right? We've got all our family of alloc things, and I've referenced them a couple times verbally, right? We know that we can mmap to directly allocate and map pages. We often see that to map some peripheral I/O if we're hacking around, not doing proper kernel drivers. We have break and sbreak where we can modify the heap size, right? So first off, mmap, right? One way that we allocate a bunch of memory from user space, right? You'll see it if you live the world of running strace on things. You see lots of mmap happening, right? When files are getting opened and so forth. So if you use map anonymous, you get allocated normal memory. The shared flag allows us to share that memory with other processes. All right, so break, why is it called break? So that's the top of the program break, legacy terminology, right? And effectively you increase the heap size with that, as we were saying, okay? Now, lazy allocation, going back to our whole lazy allocation technique, okay? We have a situation with if we look at mmap.c and do break, that it's implemented a lot like mmap, all right? So it goes in, it modifies page tables. We talked about how that happened, right? Where we modify the page tables, and then we wait for a page fault, okay? And the other thing you can do is you can pre-fault, what we talked about with mlock, right? And not have that issue where with accessing the memory, you have this long lag, relatively long lag, where it actually has to allocate that big chunk of page frames for you, right? So you can take that cost up front with mlock and then have relatively deterministic behavior once you're actually accessing the memory. The implementations of malloc and calloc, sort of the same thing. They're going to use break or mmap depending on how big the allocation is, and that's going to happen behind the scenes, right? And if you are astute, you can modify that behavior with mallopt. You could set the threshold parameter to say where one kicks in or not. That's often used in system tuning. Okay, and then finally a stack. If a process goes beyond a stack, right, CPU is also going to trigger a page fault. Okay, one of the special things that the page fault handler does in this case, right, is it's going to detect that you got an address just beyond the stack. It knows where that's at, right, and then it can allocate a new page, right. So it allocate another PFN, go into the page tables, map that in, drop it in the TLB, and remember, PFN could be anywhere. It's not physically contiguous, it's just virtually contiguous. So gets faulted in, execution continues on, and it's able to, drop stuff on that segment of the stack. You can see how that works and do page fault. That's the ARM version. And so, quick summary. Like I said, introduction. So if you're already a kernel expert, you probably know all that. But we went through physical memory, right? We looked at stock, x86 familiar memory map. We talked about virtual memory, 3 types, right? Kernel logical, kernel virtual, user virtual. Which ones are contiguous or not, right? We use kernel logical for DMA. We went through user space addressing, how processes will not have contiguous physical memory, and how swapping, page faults work to do lazy allocation and so forth. Like I say, we cover swapping, and then how those user space APIs map onto all of that. So that's it for the intro. I've got 1 minute for questions. Yes, way in the back. Okay, so the first part of the question, let me address that. So the question was, well, if the kernel always has the mappings, right, and you're talking about that kernel logical mapping that has, why do we have to wait for this expensive mapping to user space? And so to answer that, and hopefully I'm answering the right question, the reason for that is those kernel logical mappings, if we just use those, it would be just like that single address system without an MMU. And I can tell you that there's systems that in the 90s that had MMUs that running RTOSes like VxWorks, they would map with the MMU just flat address space because they had to have the MMU on for performance reasons. But you don't, without having your own process space, right, you would have to link everything in its own address space and everything. So kernel logical addresses are nice and linear and easy to think about, but you have to do these remapping for user space to have that nice world that we enjoy of that protected per user process address space where you just write a program, link it, and it'll run in any context, right? If we had all one mapping of the kernel logical spaces be just that single address space, you'd have to link your program at 0 and 1 bazillion and 2 bazillion and manage them not stomping on each other as you allocated the memory. I hope that answers the first part of it. And I'm out of time, but we can talk about the second one. Yep. Sorry, 95 slides, so.